Thanks for having me, and especially thanks for hosting me here at CREAF for a little while I'm on sabbatical. Gracias por permitirme hablar en inglés. Okay, y perdón que no parlo catalán. Okay, so our theme today, and I'm going to maybe stand here, is some work that I've been doing in Western North America, looking at changes in climate and fire regimes and how those are affecting the ecology of many of our forested systems. So, first, just to acknowledge some key collaborators that have been involved with many of the studies that I'll be sort of moving quickly through today. Cassandra Hare, Meg Krawczyk, Carol Miller, and who's also a friend of Enrique's, and Ryan Walker, who was a student of mine, Sean Parks, and then Camille Stevens-Ruman. So just to sort of explain the plan for today, first I'll talk about high severity fire and repeated fires in the Jemez Mountains, which is where I grew up in northern New Mexico, so it's a story somewhat personal as well as objectively interesting ecologically as well. Then we'll talk about sort of more broadly how changing fire regimes and climate across Western North America are affecting our forested systems. And then some thoughts on management and conservation in an era of change, with some case studies looking at some of maybe ecological information intended to support decision making as we move into the future, and then some maybe philosophical considerations at the end. So, okay, just to sort of offer the caveat that there are many differences, obviously, between the North American forest systems and those of Europe. But hopefully, we can think about some ways in which some of my work translates to these systems here. And the reason I'm here is to gain insight into systems outside of my little box, and then help inform how I think about, when I go home, the forests that I've been working with. So we talk a lot about fire regimes, and everything, almost everything we do in forest ecology in Western North America is sort of predicated on this idea of what was the pre-settlement fire regime, which is prior to the European colonialism of North America, right? So when I come here, the first thing I realize is I can't think there's no pre-European fire regime here in Europe, right? But a lot of what we do is sort of predicated on this idea of characteristic frequency, severity, seasonality, and extent of wildfire in our forested systems, and then subsequently how that's changing and what the consequences of those changes are, right? So, and just to oversimplify things horribly, we can sort of break our forests into two kinds, or two ends of a continuum. One being high severity, infrequent fire type forests. These are generally productive or sites, mesic sites, cooler sites, where climate generally limits fire. It just is impossible to have a fire, 9 years out of 10. And then you might not have an ignition the 10th year, but every 80 or 100 or 500 years, you have the conditions and things burn. And when they burn, it burns very intensely, very high severity fire. At lower elevations, we have systems that tend to be less productive. They're drier, they're warmer. These are sites where conditions are amenable to fire every single year. So we consider these are what we call frequent fire forests. However, when we have fire in these systems, they generally, there's less fuel available, and the fires generally burn at lower severity. And every time you have a fire, it removes fuel and changes fuel structure, so that it's difficult to have a high severity fire in these systems. Does this make sense? Am I speaking at a good rate? Okay, I know your English is all so much better than my Spanish, so it's good that we've done this in English. Okay, and these tend to be a classic example of this system is a Ponderosa pine system in the southwestern US, where I've done a lot of work. Okay, oh yeah, and how do we know we had low severity fires? Because these fires leave fire scars on the trees, and we can go back and say, look, how much fire there used to be until 1800s, 1900, and now we have this period without fire because of fire suppression, right? And so in frequent fire forest types, generally, we've had a large period of fire exclusion. First, it was because of a really extensive livestock grazing that removed all the grass, so those fires there was nothing to carry those fires. And then, as you probably know, Smokey the bear came and started putting fires out, really ramping up that effort mostly after World War II. You know, people started jumping out of airplanes to put fires out. And so we had this long period of fire suppression. And up here on the upper left, you can see some work from the Jemez Mounds, where I'm talking about. And all these vertical lines are fire-scarred trees at particular sites. And you can see there was lots and lots and lots of fire. And then around 1900, no more fire. And so we know there's been a lot of work showing that period of fire suppression has led to these buildup of much more dense fuels, continuous fuels from the surface to the crowns of trees. And now when we have fires, we also have conditions for higher severity fires. Okay. Also across all of our forest types, and it's the same thing happening in Europe, and it's the same thing happening in South America, and it's the same thing happening in Siberia, right? We have warming conditions. And warmer and drier conditions lead to longer periods of longer seasons where fire could burn, drier fuels, and we're having a lot more fire as a consequence of that. And just as a reminder too, I care about trees, I like forests, I like plants, but these fires bear enormous social costs as well. And we are accumulating more and more evidence that climate change is driving more fire, and it's also completely logical that would be the case. So the questions we work on is, what are the ecological consequences of these changes? So this is the first of these fires I want to talk about. This is the La Mesa Fire, which occurred in 1977. This is right where I grew up. My dad took this picture from our backyard, and I vividly remember this fire occurring. This is me probably in 1980, more or less. This is a very personal thing for me because I remember these forests when I was very young being transformed into something else because of this high severity fire. And this is a Ponderosa pine system that we think would have had, or we know had frequent low severity fires until 1890 or thereabouts, no fire. And then in 1977, this is not a low severity fire putting off that giant plume of smoke. 600 hectare fire. This was the first of a sequence of large fires, including the Dome Fire in 1996, several others. The Cerro Grande Fire is famous because it burned a whole bunch of my town down, burned a number of homes. So we had this large sequence of fires that occurred across this landscape. And in 2006, I was part of a study where we sampled data and all these different plots and looked at the vegetation. And the idea was, what I was interested in was what were the effects of these fires on vegetation. And just to show you, let's see, this is probably not worth explaining in terribly gory detail, but if you put all of these points into an ordination, we can say there were 4 approximate categories of vegetation. Forests that had little or no fire, and then as sort of you got into some areas with more fire and increasing fire severity, these areas of oak scrub, sort of a matorral, this ruderal vegetation, which is mostly non-native annual plants, some resprouting sort of weedy shrubs, and then a savanna or meadow, sort of areas that were mostly grassy with a few trees left. So 2 gradients from sort of trees to shrubs and woody to herbaceous species. So just thinking about these 4 general types. Here's an example of one of this would be sort of in between that oak scrub and meadow vegetation type. So this is what it looked like in 2006, burned in 1977. So almost 30 years later, you can see it was a forest. There's just dead snags there, but there's obviously no forest recovery here. So the question I was interested in was, well, what is the future of this site? And when we look at this vegetation, what can we project forward that there will or will not ever be a forest here again? But we didn't really need to worry about that, because then in 2011 we had another fire that occurred across the same landscape. This is the Los Conchas Fire. My dad did not take this picture. I just stole it off of the internet. And look at this. This fire, remember the La Mesa fire was like several hundred hectares. This fire was 62,000 hectares. It burned in the first 14 hours. It was burning about 1 hectare every 2 seconds for 14 hours straight. So this thing was really enormous. This is a picture of the plume of smoke from space. This is the afternoon this fire was ignited. The same afternoon this fire lit, already, you know, within that same afternoon, it already had an 80-kilometer or actually much greater plume of smoke. So this thing was really monstrous fire compared to all those others. That before we thought those other fires were big. Now we've seen what a really big fire looks like. Okay, so Los Conchas burned in addition to some of those forests that hadn't experienced fire. It also reburned some of these landscapes that had already been torched in a previous fire, right? So this is within that 1996 dome fire perimeter. You can see this area in the foreground had basically already burned once at high severity. And you can see basically now after it burned again, there's really, this is immediately after the fire. It looks pretty devastated. You can see these white stripes of ashes. Those were places where there were downed trees laying on the ground that were killed in 1996. Now they've fallen down, they're laying there, and when the second fire burns, it just leaves white ash. So, so there was still a lot of fuel laying around out there on the landscape when the second fire burned. And then these were the patches of forest that had survived that first fire, but obviously didn't fare so well during the second fire. So then our question changed. And the question is, well, how did the vegetation respond? How did those forest types that had not experienced fire change in this really big fire? How about those areas that had already been affected once by a previous fire? How did they change? So we went back in 2014 and we measured 120 of those same vegetation plots so we could say before and after how they had changed. Okay? So I'm just going to walk through each of those vegetation types. So forests, remember these were sites that really had not been impacted by a previous fire. So these areas that were previously not exposed to fire, basically, so this is that same ordination diagram, and these arrows show like where each point went to. Does that make sense? So each arrow is basically, I mean, look how far this, this point was a nice forest over here in this part of, species space, and now it's converted into something else. So we can see forests overwhelmingly changed dramatically when they got hit by this very large severe fire in 2011. And just to show you, just to show you pictures, so you believe pictures are worth thousands of words, right? So just so you believe me, oh yeah, look at this, see the bent tree right there? Okay. So now we can see this is how it changed. So here we are in 2014, and you can see, okay, that's what a high severity fire looks like, right? These are conifers, and this is an area now dominated by grasses, a lot of annual plants, but also some aspen trees, which are resprouting broadleaf species. Okay, here's another site. This is basically our perfect Ponderosa pine forest in 2006. It doesn't even really look that dense, but here it is in 2014. So, okay, so forests changed dramatically. These are areas that had not been exposed to severe, they had not been exposed to fire, or they'd really almost been unaffected by fire before, but when the second fire came through, whew, that was it. Okay, so how about some of these other types? The Savanna meadow type. So these were areas, this is kind of an exemplar of that. It's got a few shrubs, it's got a lot of grass. This site happened to have a few trees left in it. And here it is in 2006, and here it is in 2014. So really hardly changed at all. I mean, some of these dead and down fuels were consumed, but really ecologically in terms of the vegetation, the community hardly affected at all, right? Okay, how about oak scrub? These are areas that burned at very high severity in the earlier fires. They were forests. Now they look like this. In 2006, you can see there's a lot of snags here. This was basically a forest. It's been converted into this sort of shrub field. And then what happens when it burned? Basically, it looks, almost the same, except it's getting hard to even know that it was ever a forest in the past, right? So these areas, once they were converted into oak this shrub, they're very resilient to fire. They love fire. You could just give them as much fire as you want, and they will stay oak shrub. They will expand and be very happy. Okay, and then these ruderal or these weedy sites, these sites tended to change a little bit more, but some of them sort of went towards the scrub zone, and some of them kind of moved towards the grassland. But they also, you know, they didn't. The second fire didn't bring forests back. Not unsurprising, right? This is a site. This is one site in 2006. Here it is in 2014. Almost unbelievable that there was ever a forest there anymore. And then here's another site in 2006 showing kind of the same thing. This one happened to have a couple of trees that survived the fire in 1996, but here it is in 2014. And so the take-home message of all this really is that the changes that were caused by the first fire were reinforced by the second at some fundamental level, particularly where it burned at high severity and it shifted to a non-forest vegetation type. Then it sort of went even more that way when the second fire came through, right? Okay, so what we've been working on recently, and I'm not going to spend too much time on this, but is maybe thinking a little more broadly, how can we learn from this Los Conchas fire, or how what we learned from this fire might allow some broader generalizations about this phenomenon that we're calling conversion. And we have a lot of terminology already out there for describing big ecological changes, you know, state shifts or state change or transformations or regime shifts. But fundamentally what we're talking about is a change that's large, spatially extensive, and temporally enduring. We don't know what the future is. So, you know, we're saying it's converted. For all intents and purposes, it's different, and it's going to be different for a long time. So we could say that conversion in forested systems occurs when first, you know, we might have the resistance of that system overcome. So if we imagine, you know, this is ecological distance here. So low would be, you know, essentially unchanged. A trajectory of a system that had resistance basically doesn't change over time. We might have a disturbance event, but it doesn't really, it doesn't alter the system. That's a resistant system, right? If resistance is overcome, the system changes. We have a disturbance, the system shifts to something different. But if the system still has recovery mechanisms intact, that resilience is intact, over time it goes back to what it was, right? There was a fire, the trees burned, but the baby trees became trees in the future, right? But resilience can also be undermined as well. So there are different processes that can protract or prohibit tree regeneration, in which case we're on a different trajectory. The baby trees don't come back, or they come back but then another fire burns them and then they're gone, right? In that case, we have this trajectory that's something different, and we're going to have that different thing for a long time. Okay, so this is just some examples of those kinds of factors in the Western US. And probably, you know, these are all things, you know, nothing here is too new, but we're just kind of putting it all together and saying, well, number one, if you have really, really large patches of high severity fire, it can be impossible for seeds to get in there from those trees. This is for obligate seeding trees that are wind dispersed primarily. It's really hard for a tree seed to get from here into the center of this patch that might be, you know, over a kilometer away. And so in this setting, we have basically the conditions that would allow this non-forested vegetation to persist for a long time. We have many, many fires in the Western US lately that have burned at such large spatial scales that we anticipate they're going to persist as a non-forested vegetation type for a very long time into the future, right? On top of that, we know conditions are changing climatically. We're seeing warming across the board, which basically is leading to changes in plant moisture status, plant water balance. such that even if you do in some settings have the same or increased even precipitation, it's still ecologically drier for many species. And this can basically prevent trees from getting reestablished. So even though there are adult trees at this site, the conditions have changed, and we don't have those conditions that might allow the new generation of trees to get established. We're increasingly seeing evidence of this. And of course, if you look at any sort of general circulation model, moving forward into the future, we anticipate this trend is only going to become more pronounced. And then other factors are areas where we see more fire occurring. So even in systems, this is from some work up in the boreal forest where we have species that are very well adapted to high severity fire. Serotinous tree species that have cones that open when a fire warms them enough to allow the seeds to disperse. But if we have subsequent fire occurring rapidly enough, then we don't have a fire-free interval for those species to grow and reach maturity and reproduce. And ultimately that can lead to sort of conversions in these systems as well, from conifer dominated to other, herbaceous or broadleaf resprouting species. And then finally, one question that's sort of out there that is whether or not positive or negative feedbacks can somehow sort of modulate these processes. And increasingly, I think more people are perhaps looking at positive feedbacks than negative feedbacks. But a positive feedback would be one in which you have a fire that occurs and then creates conditions that promote another fire, right? And so we're increasingly finding evidence for systems where after you have a high severity fire, this photo that Alan Tepley took, you can see this area has burned twice. This side of the photo has only burned once. But basically the first fire led to this much more flammable chaparral shrubby community than the conifer forest that had been there before. So once you remove this conifer forest, you end up with a drier, more flammable vegetation type that then is sort of more primed to burn again, and basically increasing the probability of fire that also then subsequently maintains that community and expands it at the expense of the conifer forest. So it's probably not worth spending a lot of time on this, but we can put this all into a diagram and try and show what the net effect of these different processes is. And maybe in the past we know there was high severity fire, we know there was periods of successional vegetation on the landscape leading to forest recovery, and then fire leading to early successional vegetation. We know that's been going on forever, but under these conditions where we have more fire, more frequent fire, more severe fire, larger fires, and warmer and drier conditions that make it harder for trees to get reestablished, we can expect to see more large patches of non-forest that endure for a longer period of time moving forward into the future, with the potential that positive feedbacks can make those patches last even longer, or alternatively negative feedbacks could dampen these changes somewhat. This is kind of where we're at in Western North American systems. Okay, and so now I'm going to shift gears a little bit and just talk about a couple of studies and sort of this framework of, well, what do land managers do in an era of increasing ecological vulnerability? And I think this is the case not just in the forest where I work, but across most ecosystems globally. We're seeing increasing vulnerability to anthropogenic stressors, in particular climate change, right? So coral reef ecosystems, right? Maybe even agricultural ecosystems broadly, right? So different sort of, let's say, different ways of approaching change, right? First, we can think about resisting change. Can we decrease the vulnerability of a system to any change at all? Can we maintain it as it is? That would be one approach, right? Another approach might be to promote resilience mechanisms. So we can say, well, change will occur, but we can make sure the system is primed in such a way that change occurs, but it can bounce back to what its desired state, whatever that is, right? And then sort of as we get a little more maybe philosophical, in some settings, maybe we accept change. Maybe it's inevitable. Maybe it's appropriate. Maybe this system that we're seeing now is actually more likely to maintain ecosystem function and biodiversity into the future than the system that was there before. Alternately, we can think about directing change. Maybe this whole epoch of change that we're living in is an opportunity to think about, well, since it's largely driven by us directly or inadvertently or accidentally, we can think of it as an opportunity as well to shape functioning ecosystems into the future. So I'll talk about these first two a little bit with a couple of case studies, and then think philosophically about those last two for a minute or two. Okay, so just on the theme of resistance, and we know that in these historically frequent fire forest types, the fire regimes of frequent low severity fire and even mixed severity fire were the things that allowed these trees, that basically endowed resistance at the stand scale. These are trees that are, when they're mature, they're inherently fire adapted, thick bark trees. They're very resistant to fire. And at the stand level, we also had structure of basically a fuel structure that would have been prevented high severity fire and allowed a frequent low severity fire. So our question was, if we can go back to that historic stand structure, but also the historic ecological process of fire, ecological role in these systems, does that give us some resistance against this change of altered fire regimes and high severity fire occurring under extreme fire weather conditions? And it turns out, so we went back to this landscape that burned in Los Conchas. And we found some sites where they had been doing prescribed fire prior to the Los Conchas fire. So they'd been going in there and burning at very low severity or moderate severity patches of the landscape to try and reduce fuels. Also, there were areas where those previous fires, so Cerro Grande, this Lummis Fire, the Dome Fire, and La Mesa, there were areas where those had not burned at high severity and they had burned at a lower severity and probably just removed some surface fuels and left some trees, right? So our question was, if we went to those areas, particularly areas that had both low severity fire, wildfire, and low severity fire, prescribed fire, before Las Conchas, did those areas fare better? Was it more likely that forests persisted there or not, compared to areas where forests had not had any fire for over a century, right? So this combination of prescribed fire and low severity fire, in a sense, represented restored fire regimes. These are areas where there might have been 2 or 3 fires in the several decades preceding Las Conchas that burned, as we think, they probably burned historically. And so, first thing we found when we looked at, this is burn severity, this is a common metric of burn severity based on Landsat, 30-meter imagery, DNBR. So basically where DNBR is high, there's a big change in reflectance, burn severity was high. Where DNBR is low, there was no change or little change in reflectance. It looks the same from space as it did before the fire. And basically what we found was where we had this combination of prescribed fire and wildfire, forests, they didn't look very different from space. Where they had prescribed fire or just wildfire at low severity, they changed somewhat. And then where there had been no prior fire, they changed the most, right? So that was good. That's what we hypothesized we would find. And when we actually looked at our field measurements, we had data on fuels and we had pre and post fire data on vegetation. We could see that burn severity, this axis again is burn severity. Burn severity was strongly predicted by different metrics of fuels. And this is just logical, but it's sometimes in science it actually works out that your hypotheses are supported by the data, and it actually makes sense. So there, because half of the time I know it doesn't, but sometimes it works out, so it's nice. So litter and duff, these are just leaves and things, small twigs on the ground, or leaves and things on the ground. This is small twigs and small branches on the ground. These are larger, those big, large, dead tree trunks on the ground. And this is just a density of trees. And this is all, from a fire's perspective, this is all fuel. And you can see that in every case there are decently good relationships between burn severity and how much fuel there was available prior to the burn. And those relationships, you know, within each of these categories, there were different levels of fuel, with the least fuel being at the places that had already had fire in the past, because that's what the fires do, is they remove fuel. Okay, and then if you'll recall that ordination diagram that I showed before, in this case we're just looking at these areas that were forest prior to the fire. We looked at the sites that had prescribed fire and wildfire prior to Los Conchas, prescribed fire only, wildfire only, and no prior fire. And we're just sampling areas that had trees prior to Los Conchas. Again, the arrows show how much change there was. And you can see areas that had prescribed fire plus wildfire changed the least. Areas that had no prior fire changed the most. They were forest, now they're not so much forest anymore. And then these areas that just had one fire, whether it was prescribed fire or wildfire, changed sort of at an intermediate level, right? And so the take-home message here was, if we can get more low severity or moderate severity fire on the landscape, we can remove some of those fuels and create fuel structures or forest structures, reduce fuel continuity, larger spacing between trees, that when we get these big fires that come through, we're more likely to have a forest than if we hadn't done this, right? And it's fire, it's crazy. It's so much stochasticity with fire, and whether this tree lived or not might be because it was in, you know, this place where there was little fuel and it had thick bark, and it might just be because the wind blew a little bit to the left at that exact moment when the fire came through, right? So there's going to be noise. Fire has a lot of stochastic properties, but it also has some deterministic properties, and that's what we're looking at here. Okay, so now I'm just going to talk a little bit about resilience with this concept of fire refugia that we've been playing with a little bit, and maybe which are these little pockets, and I'll define it better, but these little pockets of trees that survive fire for whatever reason, being basically refugia for tree species, for other species, that might be then sort of the seeds of resilience for the recovery of these systems over time. So the refugium concept has sort of it's become popular lately. It was originally this sort of biogeographical concept that paleoecologists would say, you know, when during the glaciations, where did bears live and where did beech trees live, and then where did they expand back out following the end of the Pleistocene. But we could think about that on any time scale that we want, and in light of any ecological process or environmental process of environmental change. So refugia are defined as habitats that components of biodiversity retreat to, persist in, and can potentially expand from under changing environmental conditions. And then we've brought that concept to fire as places that burn less frequently or severely than the surrounding landscape. Operationally, for this particular project, we're just defining it as places where trees survived in a burn perimeter. So places where there's surviving patches of forest within a burn perimeter, right? So here's a nice little patch of trees that survived this fire. Maybe a single tree could even be a refugium for, it's certainly a refugium for this individual, but as well perhaps, some of the insects and birds and, squirrels and such that utilize this habitat, right? So our question is, how well do fire refugia promote resilience? And then very narrowly, how well do they promote post-fire forest recovery? And I should point out that these species, they're obligate seeding species. They don't resprout. And they're also wind dispersed species. So they don't have any serotiny in the cones. They're not just being moved, long distances by birds or anything like that. Okay, so here these are our study sites. We've been exploring these questions in these 12 different burns up in the northwestern U.S. and also in the southwestern U.S. These are burns that occurred sort of over a relatively narrow common time frame that we think was far enough back in the past that if there, should regeneration of these forests occur, we should be seeing it by now. And then these are areas that all had some of the same species of Ponderosa pine and some of these other obligate seeding firs and things like that. So the first thing we did is we developed these high resolution 1 meter imagery maps for all of the burns. And then we use that to develop a binary classification. So for any given 1 meter by 1 meter pixel, is it forest or not? And then we went to many sites, went to 686 sites actually within these burns and measured vegetation and a whole bunch of stuff, but I'm only talking about trees and tree seedlings right now in these plots, kind of stratified by gradients of how far away they were from intact forests and how abundant the intact forest was in their vicinity. So one of the first things we learned from the mapping exercise, which was really just to get us maps that we could use in the field, but then later on we thought, oh, this is kind of interesting, there's probably something publishable in here. And we finally found some review editors who agreed with us. Second try that one was. But we found that basically most of these burn interiors actually contained quite a lot of intact forest. So up to 57% that we could say, hey, well, this is fire refugia, or just patches of forest that persisted. Also, that the median patch size of these refugia was 56 square meters. So that's really, really small. That was the median patch size. So our take-home message was a lot of little patches of forest left out there in some of these burns. And this is so small that you can't see it with a 30 by 30 meter pixel from Landsat. You wouldn't find it in there. You need a higher resolution approach, or you need to get out in the field to even find these things, right? This graph just shows the distribution of patches of pixels that are either forested or non-forested as a function of DNBR, which is basically our burn severity metric that shows us that, hey, well, these areas that are considered low or low severity or are unaffected by fire tend to have lots of forest. That makes sense. But even areas that have a high burn severity as measured by DNBR, which is this Landsat 30 meter by 30 meter derived metric, even those areas still have maybe 5% forest cover within them. So these patches are out there. So then the next step was to get out in the field and say how well do these patches predict whether or not you have forest recovery. And there's been a lot of studies recently from the western US showing how forest tree seedling densities are a function of distance from surviving trees. But most of those studies look at sort of the edges of a burn, and we thought, what about these little tiny patches? Are they doing the same thing? Distance from seed source is a good predictor, but some seed sources are better than others, and some locations could potentially receive seeds from multiple different patches. So we created this other sort of somewhat more holistic metric we call it disadweighted density, but it's basically a metric that accounts for both the abundance of forest patches from, and their proximity to any given point on the landscape. And you can calculate it for using these maps. And then we use that as well as just distance to predict tree seedlings. This was one of our really nice sites that had a lot of tree seedlings. This is something we really didn't see very often. So that's one of my field technicians, and he really was enjoying himself a lot counting all those seedlings. It's always the best when you can spend hours and hours on a plot counting little things, right? Okay, so what did we find? Basically, don't worry about the numbers, but we can come up with statistical models that show how these things are related. And it turns out that our distance, weight, to density metrics were just phenomenal predictors at predicting tree seedling abundances for Ponderosa pine, other obligate seeding species, and all tree species when you put them together. And this is kind of a classic pattern from the field. Here's one of our refugia. This is down in the rodeo Chetasky burn, this huge burn down in Arizona. And we'd come on, hike towards our patch. And as we got closer, we'd find there's basically, here's our little refugium with just this ring of tree seedlings around it. So regeneration increased with the proximity to refugia as well as their landscape abundance. How much of the landscape was covered in them at any given site. So that was good. Again, this is stuff that makes sense, but it's nice when your data can support it. So the next question was, what is the patch size and abundance that best promotes forest recovery, right? Is it lots of little patches? And I know you probably can't see, this thing's got all sorts of little tiny red dots on it. Here, see? Or is it a few intermediate sized patches or just a couple giant patches? Does anyone want to venture a guess? Which gives you the most regeneration of trees, baby trees across the landscape? Lots of this or, a couple of these? I wasn't sure. So what I did was I built this fun landscape simulation model. And this was actually this is kind of where Enrique inspired me because he's done some amazing modeling in R. And we first thought we could recreate something that he did, and then we realized we were never going to be that sophisticated. So we ended up doing this, but it was inspired. This is inspired by Enrique. So anyways, hopefully you're not going to hate it too much. Okay, but anyways, so the idea was here's our landscape simulation model. We can say what's the abundance and patch size that best promotes recovery. And what we did was we generated simulated landscapes with different patch sizes and numbers. It's a 10 by 10 kilometer landscape. Then we calculated distance and these different metrics for any given pixel on the landscape. And then at each time step, we recruited seedlings into non-forested pixels based on the statistical models that we developed of how it worked in the field. And then we counted seedlings across the landscapes. And so, here's the artificial landscape. Here are these different metrics of distance and distance weighted density. And then over time, we would see those landscapes start to fill up with tree seedlings. And basically, what we found was as follows. So this is for Ponderosa pine. This is year 1, 5, 10, 20. This is the proportion of the landscape that was recovered based on a threshold density of, this one I think was 5 seedlings per 100 square meters. We said it was recovered in that case. And then we would just move forward through time. This is basically patch size, the different colors of these lines. Small patches, dark green, through large patches. So this is basically through large patches in these blues and gray colors. And you can see that, okay, first of all, this is important. What's on the x-axis? Initial proportion of forested refugia. So what proportion of that landscape was forest, right? And I said from our maps, it varied from like 20 to almost 60% initially forested following the fire. So the first thing you can see is, well, there's definitely a relationship. The more of the landscape is covered in refugia, the more forest recovery you have. Another relationship is over time, you get more forest recovery. Again, our model is supporting the intuitive relationships. And then what we found was the thing that we were interested in, the smaller patches were disproportionately better at generating tree seedlings and recovering landscapes. So again, it was those small patches that turned out to be the most important patches, and lots of small patches does a better job than a couple large patches, which is also actually kind of intuitive. But again, it was fun to make a model to explore that. Okay, and so the take-home message for all this is that these little tiny patches, and I think I showed you a photo where it had like, I'll just show it to you again because it's so cool. You know, the one tree, that is like the most important tree in this entire landscape. Well, it's the only one, so thus it is the most important one. But these are the most important trees, and I think the take-home message for land managers is they need to think about these things. They need to manage with these trees in mind because they are important. And there are ways we can think about managing for them before a fire, during an incident management when you know the choppers are out there doing their water drops and the guys are out there with their torches trying to stop the fire. How can we make sure we try and retain as much of this on the landscape as possible? And also following fire, can we manage with these trees in mind so we can have the highest likelihood of keeping them there doing what they do, which is help recover forests. Okay, but of course that's only, you know, that's if we want forests, and we'll get to that in a second. Okay, this is just a conceptual diagram that refugia kind of provide this cool link between ecological resistance and resilience, because it's these little patches, these little disturbance-resistant patches on the landscape that basically promote resilience on that landscape. So there's lots of ways we could try and make analogies about this. This is just a way I tried to express it using these traditional ball and cup diagrams. When you're near these patches or they're abundant, you're much more likely for the ball to roll back into the forested side. When you're far away, you could go either way. Maybe forests recover, maybe you end up with a non-forested vegetation. So the stability landscape is kind of tilted, as it were, based on your proximity and abundance of these refugia. So that's sort of the conceptual idea there. Okay, what we're working on now a little bit, and we have a paper that's in theory, it's accepted, it'll in theory be published I think in January or February in Frontiers in Ecology and the Environment. Basically, can we apply this concept across other disturbances, not just fires, but in thinking about droughts and in thinking about insects. We're having a lot of disturbances in our forests in Western North America. You don't have to look far to see dead trees and lots of them. How might refugia, or this concept of refugia, inform how we think about forest restoration or sustainable management of forests, or you know, into the future, in a future in which we anticipate more and more disturbances. Okay, so I talked about resisting change with restoring fire regimes. I talked a little bit about this link between resistance and resilience with fire refugia. And then just for the last minute here, I just want to say these are the things that we think about a lot. And most of our forest management in the US and in Canada is kind of the fundamental assumption guiding that management is that we want forests forever into the future, right? So that's where this whole, that's a lot of the sustainable yield forest. A lot of our legislation is based on this concept of sustainability of forests into the future, right? And so managers are really stuck in this idea. We want to resist change, or we want forests to be able to recover. We want healthy, resilient forests. And that's probably okay for now. But moving forward into the future, we may find ourselves in situations where change is impossible to avoid, right? Where, because at least the way funding works in my country, there's only a little bit of resources to fight a huge problem. The scale of our solutions are completely mismatched with the scale of our problems right now. And so this kind of provides some other, what do we do with that? Maybe we can think about accepting change or directing change, where we might not have the choice of maintaining systems in the future. And of course, with climate change, we know that many of our species, we're moving rapidly into a complete disequilibrium between where species are found and what their climatic niche is, right? And so this is just my last sort of 2 cents. When do we resist, accept, or direct change? Well, I don't know that we're ready to start answering this question, but we can think about what that answer would require. It really requires a better of what is the likely direction, rate, magnitude of change. Where are systems likely to change? To what are they likely to change? And these are questions we don't really have good answers to yet. And then even more fundamentally, perhaps, what is our capacity to even resist or direct change? Where can we even resist it? What sort of resource investment would it require to maintain this forest on this site for the next 100 years? We don't necessarily know. And if we can't, what is our capacity to, to move towards some other alternative? And then finally, as we improve our understanding, I think we fundamentally lack an ethical framework for this epoch of change. Like, what is to guide us in making these decisions? These are, I think, novel questions for humanity to be addressing sort of at a global scale. And so, I think increasingly about environmental ethics, intergenerational ethics. Our CO2 emissions, our best guess is that they will have profound impacts for the next 10,000 years, right? More or less, let's say 400 human generations, as well as all the other species on Earth and their evolutionary trajectories, right? Somehow or other, we need to broaden our ethical sphere to, both include, non-human organisms as well as, humans that are yet to be born many, many generations down the road, right? So just a few thoughts on that. You may have heard, I don't know if you've heard this principle of seventh generation as this idea from the Iroquois Nation, which is one of the indigenous groups of North America, but their principle was the seventh generation, that the chiefs would have to take into account their effects on the seventh generation, not just, the short term. And I wonder, how many generations down the road are politicians thinking about currently when they're our elected leaders? Are they thinking even one generation? I don't know. I'd be surprised if they're thinking about the seventh generation. Okay, that's about it. Lots of acknowledgements, and there's a lot of people I haven't acknowledged, but that's just how it goes, I guess. So, all right. And questions? I don't know where we're at with time. Are we over time? I heard someone's watch beep, and then I thought, oh my God, is it already? Okay.
So I'm going to start. I'm curious to the results you presented on prescribed fires and wildfires promoting resilience.
Yes.
Not losing the forest were more effective than the natural wildfire in the landscape.
Yeah.
Do you think that's because the forest is already changed by fire suppression, or that the fire regime now it's not effective given that the climate has changed to preserve?
So why that the prescribed fires were better than wildfires?
Prescribed fires plus wildfires
Yes.
were better than wildfire alone, which
Yeah.
means that it would be the natural fire regime from the... So why
Right.
that's what prescribed...
Well, right. So the thing with the prescribed fires is that land managers can be very deliberate in what the fire is intended to accomplish, right? And with wildfire, it's kind of happenstance. Most wildfires are burning when conditions are dry and the wind is blowing one way, and the effects are, I think there's a lot more variation in the effects of wildfire, if that makes sense. And in the settings where they had done prescribed fires, it was very deliberate. Okay, here's our objective for this fire, and they're going to go in and burn in, October or November, which is in our, in this system, like it's cold, it's not as dry, and they can be very deliberate and also very effective in if you want to go out with a prescribed fire and you have people with drip torches, they can burn, every single log that they want to burn ultimately, if that makes sense. They can torch a tree or leave it if they want, right? And I think my guess there is that the prescribed fires are so much more targeted and deliberate that they can ultimately be more effective in changing fuel structure. Whereas maybe wildfires are coming through and they're creating patches of openings, but they're also leaving all sorts of dead trees laying everywhere. And hey, that can be, it reduced fuels, but it also changed fuel structure in a way that might not be as effective at reducing high severity fire.
What's the current strategy for prescribed burns
What's that? What's
the strategy right now? Are people really attempting to do a lot of prescribed burning?
Oh, I think it comes and goes, right? There's a lot of interest in prescribed fires, but it's very risky. And in Colorado, for example, there was a great prescribed fire programs, and then it only takes one prescribed fire to get out of control and burn down some people's houses, and then nobody wants prescribed fires anymore. So it tends to come and go. More so now, we're seeing a shift towards what we're calling, well, there's different names for it, but resource objective wildfire, or allowing wildfires to burn when we think, oh, maybe this fire can go do its natural thing. But it's a very risky business, right? If you want to remove fuels across a large landscape, a fire is the cheapest and quickest way to do it, but it's the most difficult to control. And for land managers, it's much easier to put a fire out or say, no prescribed fire. You're never going to lose your job for making that decision. But if you decide, let's let this one go, then there's a risk that's involved there. Something goes wrong, there goes your career. Individuals can be sued. I mean, it's a very sketchy thing. So it comes and goes. We all know what needs to happen, but there are other reasons why it's not happening nearly at the rate that it should. And a lot of it is social factors, right? It's easy for ecologists to go say, oh, this is what we should do here. This is what the science tells us. But if you're the guy who has to do that, or the gal who has to do that, you got to listen to your boss. You got to figure out where where your paycheck's coming from, what the public wants. It's much more complicated. So it comes and goes.
Plan to study the grazing or another animals or another ways to remove all the grass and
to reduce fuels, or
just to check if there is another ways not using fire to
so people are, right? And so there are studies. So in some places, so for grazing animals, there's experiments using goats, because goats eat everything. And so if you have, concentrate the goats on a certain area, they'll eat everything eventually. They'll remove all the fuels. So people are experimenting with that a little bit, but it still sounds kind of crazy. And so the main strategies they use are going in there with crews of people to cut things down and make piles and burn the piles, or we also have these big machines that do this mastication treatments. I think they happen here in Spain too. Oh, we'll just go and mulch all the fuels and create wood chips everywhere. But those things are very expensive, and you can't get them everywhere. So ultimately, they're far less effective. And also, if your goal is to restore functioning ecosystems and ecological processes, well, then it's a little bit antithetical to that goal. If you can't allow fire to ultimately go do what we think fire was doing, and maybe we want it to do again, depending.
The folks you studied in this, all the results, are they natural stands, or somehow did you categorize, manage the planted, and then?
For any of these studies, or? I would say that where I'm working, most of these landscapes are the regeneration is natural. They're the history and the amount of human intervention has been very little compared to, say, here in Europe, right? And so the vast majority there was sort of things were happening, and natural is, there were Native Americans doing things, but the trees that are there were generated from seeds that fell from another tree, right? There are some areas where there was logging that took place a long time ago, but not very much recently. And we focused most of these studies, the refugia study in particular, we only went to areas where, you know, we knew there hadn't been logging recently, where we knew there was no salvage logging after the fire, those kinds of things.
Right. So, yeah, natural, ecological processes.
So
yeah.
for the most part, much more natural. I mean, there's nothing natural anymore, right? Because the atmospheric chemistry has changed, right?
But there are always like, you know, boundaries between.
But much more natural, yeah, than as natural as you know we could. And generally, that's much more natural than, you know, what you would find here.
Okay.
The thing you said before about cutting off the fuel, and I think it's worse because if you take off the fuel and for the same is worse because of the erosion, you know, when it rains,
Yeah.
it gets like really flooded. So what are the pros and cons of taking the fuel? Because I think it will be worse if you take it off. You know?
Right. So you're saying like those heavy woody, those down woody fuels, better to leave them or not? And the answer is it depends, right? What's the problem that we're trying to address? Are we trying to reduce fire hazard? If so, that's fuel. Those fuels will promote fire, right? But in some settings, maybe we want to keep them for that exact reason, right? So these are the kinds of trade-offs that we definitely have to be aware of. I would say, you know, in this system here, you know, having all that grass and having shrubs and having intact vegetation is essential to preventing erosion. And if we want that stuff, well, we probably want less of those woody fuels because that's the stuff that's going to burn more severely and impact those plants, right? But there are trade-offs, right? And so like this idea with the mastication, oh man, we'll just put wood chips everywhere. We'll mulch it all into wood chips. Well, in theory, that will help reduce erosion. But again, your fuel is still there. It's compacted. And then when it burns differently. So these are good. That's a great question. It's very complex. And it, you know, this is true in ecology, right? I tell my students this. The answer is always, you can answer any question on the test. Well, it depends. You just have to be able to say, well, it depends on what, right? Otherwise, yeah, well, then we're not going to get very far. But there's always these complex trade-offs, right? So in this refugia study, maybe these little patches are great. I'm going to say we should have lots of little patches of trees if we want forest recovery. But there are probably species that would do much better with a couple large patches, just, right? We have sort of island biogeography tells us, well, little islands are not always the best for other species, for other ecological processes. All right.
Thank you very much everyone for coming. And thank you, Jonathan, for
All right, thank you.